Now, the dilution law for normal solution. Normal means in case of which normality is given, right? See, in this also, let me give you two things. N1 V1 is equal to N2 V2. Just like what we have seen in case of dilution law for molar solutions. Now, these are the normality and volume of the solution before dilution. And these, in fact, are the normality and volume of the solution after dilution. Okay. So, Adira Vishnu. Now, see, this can actually be used for calculating normality of the solution obtained after dilution, right? We can actually take example of the same old type. Say we have 100 ml of 0.1 N, I mean decinormal solution. Now, supposing if 900 ml of water is added, what is the normality of the resulting solution? The final volume is V1 plus water, right? This, of course, is V2, which is nothing but V1 plus water. Okay. So from this, we can calculate N2. It will be 10 times. N2 is, of course, 0.01 normal. You got centinormal solution after dilution. So this is what for we can use the relation. Okay. Now, let us take the same relation and make use of that in a different way. Okay. See, the same relation can be used for calculating volume of water to be added to get a solution of required concentration, desired concentration. Now, let me take an example. Consider the same 100 ml 0.1 normal solution. Now, would actually like to make it 0.05 normal solution. What is the volume of water to be added? Now V2 is equal to 200 ml. We know that V2 is V1 plus water from our previous discussion. Therefore, volume of water to be added can be given as V2 minus V1. Now that comes out to be 200 minus 100. So 100 ml. Or else you can use this relation. V2 minus V1 is equal to N1 minus N2 by N2 into V1. Right. Now, N1 is 0.1, N2 is 0.05, again 0.05 into 100. So this is of course 100 ml. Okay. That's it. Next. Now the interesting ones. Rule of molarity. See, this can be given as M1 V1 by N1 is equal to M2 V2 by N2. Now, these are the molarity, volume, and number of moles of the first reactant of a particular reactant of another reactant. Now, these reactants may be, if suppose this is an acid, this will be a base. Likewise, if this is an oxidant, this would be a reductant, right? That way, molarity, volume, and number of moles of the first reactant, molarity, volume, and number of moles of the second reactant. You know, finding the number of moles is also very simple. Let me give you one or two examples here. Now, without writing the equation itself, we can find the number of moles. Look at this. See, for this acid, we know that the basicity is 2, right? Now, for this base, acidity is 1. Simple. Acidity is the number of moles of acid. Basicity is the number of moles of the base. You need not write the equation. You need not balance it. Okay. So simply take this acidity as the number of moles of acid. Basicity as the number of moles of base. Right. In a similar way, change in, okay, let me take one more example. KMnO4 oxalic acid. See, in acidic medium, KMnO4 gets converted into MnSO4, during which manganese is reduced. So this is an oxidant, the one that undergoes a reduction, or the one that oxidizes others, is an oxidant. Now coming to this, this oxalic acid is oxidized to carbon dioxide. See, there are two carbon atoms in the reactant. So we have to consider the same number of carbon atoms in the product. Remember, you have to consider the same number of atoms as are present in the reactant, even in the product also. So in this case, it is 2 into plus 3. In this case, it will be 2 into plus 4. Now, overall, anyway, this has undergone oxidation. So is a reductant, right? In this case, change in oxidation state can be given as 5 units. And here in this case, the change in oxidation state is 2 units, right? Plus 6 to plus 8. Now remember, this change in oxidation state of the oxidant is the number of moles of reductant. Similarly, the change in oxidation state of the reductant is the number of moles of oxidant. Okay, simple. Take this 2 here as the number of moles of potassium permanganate. Take this 5 here. This is very interesting. We need not go for the equations. We need not balance the things. But still, we can write the number of moles. Yes. Now let me take rule of normality. See, this is N1V1 is equal to N2V2. In fact, this can be written as N1V1 by E1 is equal to N2V2 by E2. Just like the M1V1 by N1 is equal to M2V2 by N2. In this case, we can actually take N1V1 by E1, where E1 refers to number of equivalents of the first reactant of a particular reactant, and E2 refers to the number of moles of the other or the second reactant. But generally we avoid these two. But why? Let me tell you. Now, let us consider a very interesting example. Now, based on our previous knowledge, see in this case, the basicity is 3, and in this case, the acidity is 1, right? Now, acidity is the number of moles of acid, basicity is the number of moles of base. So, let me say that 1 mole of phosphoric acid reacts with 3 moles of sodium hydroxide. Therefore, the mole ratio or molar ratio is 1:3, right? Okay. 1 mole is reacting with 3 moles. We got the molar ratio as 1:3, and now let us check the ratio of their equivalents. Okay, how about this? 1 mole of phosphoric acid is nothing but 98 grams. It's gram molecular weight. Similarly, in this case, it is 3 into 40 grams, nothing but 120 grams, right? 98 grams of phosphoric acid is reacting with 120 grams of sodium hydroxide. Let us convert the two things into their equivalents. Therefore, number of equivalents of phosphoric acid is the molecular weight by, of course, its equivalent weight. We know that the equivalent weight is molecular weight by basicity, right? So this comes out to be 3. Then the number of equivalents of sodium hydroxide is given weight by equivalent weight. 3. Now, therefore, the ratio of equivalents is 1:1. Isn't it? 3:3, nothing but 1:1. So this is an important thing. See, generally, the molar ratio may or may not be 1:1. That is the reason why we have taken N1 and N2 in rule of molarity. But you know the equivalence ratio is always 1:1. This is 1. This also is 1. So they need not be taken. The point to be noted here is, let me write, mole ratio may or may not be 1:1. It may be anything, but equivalence ratio is always 1:1. And this is the reason why we find it more easy to go with equivalents rather than going with moles. we can simply take their equivalence ratio as 1:1 and just get into the problem solving. Because if you go with mole ratio, then you need to actually first learn the ratio of the moles in which they are reacting. Okay. So this is a very interesting discussion. Now let us go for the calculation of concentration of the mixture. Okay. I have so many varieties. Let me give that relation. See, this particular relation is used when acidic or basic solution of the same solute are added. Very interesting. It's because of the basicity and acidity thing. See, in this case, remember to take only the solutions of the same solute. Now, this is molarity and volume. Okay. Supposing if we have 100 ml 0.1 m solution and of course 200 ml 0.2 m solution, then the resultant molarity can be calculated as this. Simply when two solutions are added or mixed, this is how we calculate the final answer. Okay. Then coming to the next thing. Now there is a relation of this type. Now this is used in case of solutions solutions of the same solute are mixed and diluted. That is interesting. Mixed and diluted to a different volume. The different volume is your V3. V3 is nothing but V1 plus V2 plus water what you have added. Now supposing if you have added the same two solutions and the final volume is made up to a liter by adding 700 ml of water. Look at this. So this is 100 plus a 200 plus the 700 ml of water what we have added. Okay. So the first case is simply when the two solutions are mixed. Second one is when the two solutions, not just two, you can take any number, but remember they must be of the same solution. When you go for molarity, remember they must be of the same solution. Okay. But when we go for normality, of course, we can take different solutes, but they must be of, say, if you are adding, they must be either of acidic or basic. But if acidic and basic solutions are mixed, then it will be different. We'll see that. But for now, remember, the first case is only when the two solutions are added. The second case is when the two solutions are added and diluted.